Okay. And you've got my shared screen. I think, yeah. What I wanted to do today was just sort of keep going, moving through this chapter. We're going to talk about implicit differentiation. We're going to finish this chapter on Wednesday with higher derivatives, and then I think we'll be in pretty good shape to take our next test a week from tomorrow. And then on this test and all the tests that come after this, so Chapter 3, Chapter 4, you can make a note card to use on the test.
Sorry, just writing on the board.
Okay. You can make a note card to use on the test that's subject to some rules, so it could be no bigger than a 5x8, and you can use both sides, or you can measure out an equivalent amount of area on a sheet of paper. That's fine. It has to be handwritten by you, nothing typed out, no photocopies. It cannot contain worked out examples, so you might include, things people tend to include are like what the limit definition of a derivative is, or like what the product rule is, or something like that. And if you don't use a note card, you'll get 5 points, 5 bonus points. So what I always tell people is just make a note card. Make one. You can hand it to Mrs. M at the beginning of the test, and you can decide at any point in the test if you're better off with your note card than you are with those 5 points. So take the time to make the note card. Everybody can start off like going for the bonus points, and you can decide if you want to use your card later, during the test. Before we talk about implicit differentiation, are there questions on the exercises or anything like that? I haven't graded the quizzes yet. There are 2 people who hadn't taken it yet, so I think that's happening today. So I should have those quizzes graded later today and up on Canvas just as soon as I can.
Although neither of them are here today.
Oh, okay, all right. Well, okay, then I'll catch up with those 2. And I promise I won't make you wait forever to get your quizzes back, so maybe it'll end up being tomorrow. Are there questions from anyone? Okay, I'll have a problem set posted. Now, I can't remember if I actually already posted it, so which is certainly plausible. I did. Okay. So problem set 2 is already posted. And so you can take a look, before you get your hands on a hard copy. The PDF is there. It'll be due a week from tomorrow. So I guess if there aren't any other questions, we'll go ahead and get started. I don't know if today's material will take the whole time, so I want to make sure that if you have questions that you take time to answer them. If there's something that is not clear as we're going through examples, we do have time. You can stop me and we can go through it again. So this section is called Implicit Differentiation. And it's basically like an extension or an application of the chain rule. So I might call it the chain rule part 2. So you'll recall that when we learned the chain rule, before, the general chain rule was like, dy dx is equal to dy du times du dx. And this is basically how we're going to see the chain rule play out in this implicit differentiation. So I guess first we'll just talk about the word implicit, how we mean it here. Usually, and up until now, all of our functions have been explicit functions. They're functions where, like, for example, y equals 5x squared minus 7. That is an equation that's set up where we have y by itself on one side and all of the x's on the other side. So it's set up in a way that just spits out the y, right, as an output once we know what x is. And that's what we would say, that x is an explicit, or y is an explicit function of x. An equation that defines a relation between x and y, but is not explicitly define y as a function of x, is called an implicit function. So just think of equations with x and y that may or may not define y as a function of x, right? For example, this is a line, right? There's a linear equation, 3x plus 2y equals 6. That's implicit because it's not set up to have y equals some function of x. Now, in this example, there is an explicit form. We could do a little algebra. Here's the explicit form, right? So these are equivalent. So this is implicit here. And as it turns out, we can do some algebra, and it does define y explicitly as a function of x. Not all implicit functions define y as an explicit function of x. For example, in part B, y squared plus x equals 3. That's an implicit function. That defines a relation between x and y. We know just looking at the equation, it's a parabola. It's a parabola that's oriented, horizontally, right? Because the y is squared and the x is not. It defines a relation between x and y. Now, it doesn't define y explicitly as a function of x, because if we try to solve for y, we get two different values, right? We end up having to take a square root, and that means we have the plus or minus business here, so that's why we have these two different equations. And now some implicit functions, we don't even have an algebraic option to isolate the y. Like this equation here, y to the fifth plus xy squared plus 3x squared equals 5. Try as you might, I think you'll be hard pressed to get that as a y equals, just y by itself and only x's on the other side. But it still defines some curve in the plane. It's still, if we think about this parabola here, that is that's a parabola that's oriented, horizontally. However it looks, something like that. In fact, I think it might actually go the other way. That's beside the point. The idea is we could see it doesn't define y explicitly as a function of x because it fails the vertical line test, right? If I draw a vertical line, it'll cross the curve more than once. However, in calculus, one of the central concepts and questions that we work with is how is this changing? What is the slope of a tangent line? Even though it doesn't define y explicitly as a function of x, I might still want to know, well, at this point right here, what's the slope of the tangent line? So we still have a reason for wanting to find dy dx. And that's what we're going to focus on in this section. How do we take an equation that defines y implicitly as a function of x, or an implicit function, and how do we still find dy dx? So we're going to start off with an example. With implicit differentiation, it's all about knowing what variable we are respecting. And in this section, it's always x. In some applications, as we'll see in the next chapter, it's all about respecting time, like finding a time rate of change. But for the problems that we encounter in this section, it's primarily going to be ones that we can interpret as slope of a tangent line, so dy dx. And the upshot is, anytime you're taking the derivative of a term that's not an x term, maybe it's a y term or a z term or something, you use your rules as usual, but you have to follow up by multiplying by the derivative of that variable with respect to x. So kind of coming back up here to this chain rule right here. And we're going to see how this works with an example. So our equation that they give us here is y squared plus 2x squared equals 5. And they want us to find dy dx. Now in mathematics, when we're working on an equation, we could do the same thing on both sides of an equation, right? If I want to add 2 to both sides, I can do that. If I want to multiply both sides by -5, I can do that. If I want to take the log of both sides, I can do that. And if I want to differentiate both sides with respect to the same variable, I can do that. So we are going to differentiate both sides with respect to x. Our first term is y squared. What we're going to do is use the rules as we want to, right? As it seems like we ought to be able to, right? This is something raised to a power. So we're going to use the power rule. This says I'm going to bring that power down in front. and then y to the 1 less power, so we just get 2y. Now here's the chain rule, right? How the chain rule plays out in implicit differentiation is, oh, but I'm respecting x, and that's a y, so I have to multiply by dy dx. This right here, this is the chain rule. Then I move on to the next term, and I've got a 2x squared. So I take the derivative of that. What do we get? 4x, yep. Now I'm going to write out how the chain rule might look here. Normally we always leave this off, all right? So if you're thinking, oh, but that's an x, I don't need to, you're absolutely right. But you could think of using, applying this chain rule all the time, every single time if you want. I'm respecting x, and that is an x, so I would say, oh, times dx dx. But dx over dx is just 1, and that's why we always leave it off. That's why we just think, oh, I don't need it then. On the other side of the equation, what do we get?
0.
Just 0, yep. All right, so the dx dx we know is equal to 1. Now I have this equation. I'm just going to clean it up a little bit. 2y dy dx plus 4x equals 0. Okay. They said find I've taken the derivative. We have differentiated. Sort of that calculus part where we take the derivative, that's over. We're not done yet because this problem says find dy dx. My goal is to get dy dx equals. So the rest of this is algebra. Let's solve this equation for dy dx. We'll subtract 4x from both sides. So we have now 2y dy dx is equal to negative 4x. And now it's all over but the shouting. To get dy dx by itself, we just divide by 2y. I'm going to bring this up here. We get dy dx equals, and if we do some reducing, the 2 cancels there, so we get minus 2x over y. Now that's pretty common when we find dy dx with an, using implicit differentiation. Sorry, I just screwed that up. Let's see, minus 2x over y. That we end up with an expression that has both x's and y's, right? I couldn't get y written explicitly, or dy dx written explicitly as a function of x. That's not uncommon. We couldn't get y written explicitly as a function of x in the original equation, so it's maybe not surprising that the same holds for dy dx. Now, if we think about what this means, this equation they gave us, y squared plus 2x squared equals 5, what kind of curve is that? What's that?
What?
It's an ellipse. Yeah, they're both squared, right? Both x and y is squared, but their coefficients are different. And if we just do, I'm not going to get this perfect. I could tell that it's centered at the origin because there's no plain x term or plain y term. And it's oriented vertically, so, this looks something like this, right? I don't need it to be perfect. It looks it looks only very roughly like that, actually. In fact, that's bugging me, so let me just try to do a little bit better. Okay. So so this is what they wanted us to find, right? So we have dy dx. Note that in order to find the value of dy dx, I need to know the both x and y coordinates, right? I need the value of both x and y to get a numerical value for dy dx. That kind of makes sense because if you said, or anybody said, well, what's the slope of a tangent line when x is equal to 1 or something, okay? I would have a hard time answering that. I would say, well, which of these points do you mean, right? We actually, in fact, do need both coordinates in order to define which point we're talking about and find the tangent slope. Okay, so that was sort of like a simple-ish example to kind of get us started. We're going to do a couple more examples that are a little bit more involved. We are going to have to be on the lookout for times when we have parentheses to a power or when the product rule might be needed. Before we go on to the next one, though, are there questions on this one? All right. Okay. So, and when I'm starting a problem, I just like to kind of scan the equation and just sort of make a mental note of any, any special considerations I need. There's definitely no parentheses to a power I need to worry about here. But what's going on here? Say that again. It's a product rule. You have to like really speak up because you don't always get picked up by the microphone and.
Nobody's talking.
Oh, okay, all right. Well, then I'm just imagining things, or maybe it's wishful thinking. I think that's what it is. I'm just hoping somebody's going to say something, and so it is a product rule. Look, we're multiplying x times y squared. We're multiplying two things. We think of y implicitly as a function of x. So we're like multiplying two functions together, basically. And so if we set this up, our product, our f function is equal to x. That means f prime is just 1. Our g function is y squared. So what is g prime? Say that again.
Y.
2y. And what variable are we respecting? So we're finding dy dx here, right? So in the very beginning, we know that we are respecting x, and when we find g prime here, we're taking the derivative of a y term. So the chain rule says, what do we multiply by?
By dx.
Yeah. So we've got our product rule kind of set up here. We've got the pieces we need. So when we get to that term, that's where that's where we're going to turn. So I'm just going to write this equation again and get started. Now we're going to take the derivative on both sides with respect to x. We start with the first term, 3y to the fourth. What should we get?
12y to the third.
What else do we need?
dy dx.
dy dx, because that's a y term, and we're respecting x. Now we got to, now we're at this product here, and we already did this work on the side, so we're just going to put together our g times f prime, that's y squared times 1, plus fg prime, so that's x times I don't know what's happening. Hold on a second. I've got to My OneNote is getting a little crazy. I'm going to close this and open it again. Okay. So f times g prime is x times 2y dy dx. Great. So there's the xy squared term. What comes next?
6x to the second.
Good. Now what?
He times it to dx over dx.
Oh, sure, yeah. Yep. And this is the thing that we can include or not include because, of course, dx over dx is equal to 1. So we'll actually drop the dx over dx in our next line. And then, hold on. I did not plug in my laptop. Let me fix that. That would be bad. Okay. And then, so there's the 2x cubed term, and then the rest are constants, right? So it's really just equal to 0, right? The 6 goes to 0, and then it's equal to 0. So here we are. We've taken the derivative, right? The differentiating part is over, but we haven't found dy dx yet. So we still have a bunch of algebra to do, but lucky for us, we're pretty good at algebra. So what I'm going to do first is just kind of clean up the equation a little bit. We want to solve for dy dx, and we can do this. This equation is almost linear in dy dx. Like the techniques that we're going to use to solve for dy dx are just like the techniques we would use to solve a linear equation. I'm going to get all my dy dx's on one side and everything else on the other side, and then we'll kind of combine like terms and do some division. So we can subtract y squared and subtract 6x squared from both sides. Now everything on the left side has a dy dx, so our next move is to factor it out. And after we've factored it out, really the only thing left to do is to divide by the stuff in the parentheses. And now we have our result. You could leave it like this, or, on the bottom, I guess we could factor out a 2y. And I would say it's kind of up to you because there's no common factor up top, so it's not gonna like cancel anything. Sometimes it's nice to have a denominator in factored form. I'm just going to pause there for a moment, sort of give us all a chance to kind of assess, take a look at what we did, and see if there are questions on any part of this process. Let's do another one. We're going to find dy dx. Here's an implicit function. Right at the beginning here, we have another product. 2x cubed times y. Right, when we're multiplying different variables together, we have to treat that like a product rule. So I'm going to go off to the side and set this up. Our f function is 2x cubed. So let's see, applying the power rule gives us 6x squared. Our g function is just y. What is g prime? 1. And what variable are we respecting?
X.
Right, so what do we have to multiply by?
Right, yeah.
Yeah. And that makes sense, right? So here's what we said, is that if g is y, then its derivative is dy dx. And that makes sense. So there's our product rule. Let's get started then. If we're taking the derivative, we'll start right off with the product rule here. So g times f prime is y times 6x squared. F times g prime is 2x cubed times dy dx. So that takes care of the first term. Next, we have a parentheses to a power. So we're going to have to be careful here. How do parentheses with a power, how does that usually work? Like, who wants to start us off? But generally, it's going to work mostly the way you think it's going to.
Turn off 3 parentheses y squared plus 2 to the second x.
Y squared what?
Plus x.
Yeah. And then to the second. Good. So that's basically how parentheses to a power works. And then comes the chain rule, right? Then we have to say, let's multiply by the derivative of the stuff inside. So now, focus on what's inside the parentheses. What is the derivative of that stuff?
2y. Plus 1.
You're very close. What goes here?
dy dx.
Yeah. Now notice I needed to put parentheses around this, right? There was more than one term to the, to the derivative of the stuff inside, so I have to kind of group that. So there's the derivative of the highlighted term now. And now we're on the other side of the equation, which is x to the 4th. Now that seems pretty simple in comparison. Just use the power rule, we get 4x cubed. So so this one had a product rule, so did the last one. This one had parentheses to a power, and the stuff in the parentheses had a y in it, which means that one of the places where we see dy dx show up for us is inside a set of parentheses. So what I'm going to do here, or at least sort of my approach on these, we need to solve for dy dx, right? We've finished taking the derivative. The rest of it is algebra. We just have to be careful. We need to extricate that dy dx from being inside parentheses, and we'll do what we usually do in algebra to get that done, which is the distributive property. So we have this stuff, right? This 3 times parentheses squared. That's being multiplied by the stuff in the parentheses. And to get that dy dx out, I'm just going to distribute it to each of these terms. So on our next line, I'm going to clean up those first two terms as well. So I've got 6x squared y plus 2x cubed dy dx plus. Now when I distribute it to the first term, I'm going to have, let's see, 3 times 2 is 6. So 6y times this parentheses squared dy dx. I've just chosen to throw my dy dx at the end of the term instead of at the beginning, but it really doesn't matter. plus, now I'll distribute it to that one term, so 3 parentheses y squared plus x squared. On the other side we have 4x cubed. Questions on how we executed that part? And so now, I mean, this is progress. It looks uglier as an equation, but this is progress. I could tell it's progress because now the only places where dy dx shows up are not trapped inside a set of parentheses. I've got a dy dx here and here. I want to kind of keep those. There's no dy dx's on the other side of the equation. So I want to keep my dy dx's on the left side, and anything without any terms without the dy dx, I'm going to throw over on the other side. So I'm going to subtract 6x squared y from both sides. I'm going to subtract this last term, 3 parentheses squared. And when we do that, on the left side, we've got 2x cubed dy dx plus 6y parentheses squared dy dx. And then we have 4x cubed minus 6x squared y minus 3 parentheses squared on the other side. What comes next in this process?
Factor out dy dx.
Perfect. Right, we've got all of our dy dx's on one side, so let's factor it out. Inside now we got 2x cubed plus 6y parentheses y squared plus x squared. And now it's all over but the shouting, right? We're just going to divide by the stuff in the parentheses there, the big set of parentheses, to get dy dx by itself. And this is, you know, one kind of gnarly looking derivative, but, you know, not only do we need to write it using both x's and y's, but also it's just, you know, complicated. But maybe we're not so surprised given how our original equation looked. Sometimes this happens. And yeah, we could factor out a 2 from the bottom. I'll leave that up to you. I would think of it as kind of optional just because there's not a common factor of 2 up top that we could cancel it with. Questions? Okay. All right. Then I think we've got one more to do. Okay. So here they've asked us to find the slope of a line tangent to this curve. They've graphed it for us. This is called the Folium of Descartes, I think. That's just bonus information. But we want to find the slope of the line that's tangent to this curve at the point 2,4. So it does go through the point 2,4. They've drawn that tangent line for us, and we want to find its slope. It looks like we should get a positive number, right? I mean, I guess that's one thing we could kind of tell just by looking at it. Let's begin. Here's our equation. X cubed plus y cubed minus 9xy equals 0. Who wants to start us off?
Product rule for the 9xy.
Say that again.
Product rule for the 9xy.
Good. Okay, you said product rule for the 9xy. I like that, and what I'm doing is I'm kind of just putting this in a box and just keeping in mind that we're subtracting that term. So we can think of it as adding a negative 9xy or subtracting 9xy. I'm going to think of it as subtracting 9xy, going off your suggestion. Either will work, but we just want to be mindful of that negative sign. So if we're setting up the product rule for ourselves, then our f function is 9x. What's f prime?
9.
Just 9. Our g function is y. What's g prime?
dy dx.
Great. Okay, so now we have that set up, so it's ready for us when we need to use it. Let's take the derivative. What do we get?
3x squared times dx dx.
Sure, yep.
Plus 3 squared as dy dx.
Yep. And so now we're at the product rule. And keep in mind, we thought we saw this as subtracting that product. So I'm going to just pull down the minus sign here. And then the product rule, I'm going to put in a set of brackets or parentheses. So g f prime, g times f prime is just 9y plus f times g prime is 9x dy dx. Right, and then this is all equal to 0. So I just want to be kind of mindful of that negative sign because, of course, we're going to have to distribute that. We're going to be subtracting both of those terms. And maybe that's what I'll do next. And also, let's see, dx is equal to 1. So just cleaning this up a little bit, I have 3x squared plus 3y squared dy dx minus 9y minus 9x dy dx equals 0. So we don't have dy dx's, any dy dx's trapped in parentheses right now. And I think that means, you know, in all of our terms are on the left side, so I think that means we're ready to kind of isolate that dy dx term. Why don't we go ahead and subtract 3x squared and add 9y to both sides. What comes next?
Factor the dy dx.
Yeah. We're going to factor that out. Now, if you actually look at all the terms on both sides, there's a common factor of 3 everywhere. So I'm going to factor that out too, because that'll cancel. May as well just do that now while we're doing some factoring. So I'm going to factor out a 3 dy dx. And then we have inside y squared minus 3x. Over here, I'm going to factor out the 3 as well. 3 times 3y minus x squared. And then we're ready to divide. I'm going to divide by 3 times y squared minus 3x. So the factors of 3 cancel, and then we get 3y minus x squared over y squared minus 3x. So there's the expression for the slope of a tangent at an arbitrary point that's on this curve. And then the only thing left to do to finish this up is to evaluate it, to figure out what that slope is at the point 24. Keeping in mind, if we kind of go up and take a look, we should expect to get a positive slope, it looks like. So dy dx at the point 24. So we've got, let's see, I'm going to put in 4 for y, so 3 times 4 minus 2 squared over 4 squared minus 3 times 2. So that's 12 minus 4 over 16 minus 6, which is 8 tenths or 4/5, and that is positive. That kind of jives with what it looks like. Questions? Okay. All right. That's as far as I wanted to get today. We have some practice exercises that we can work on. There's a problem set that's posted to Canvas. You have a note card you can begin thinking about what you want to include. What are some things that you might include on your note card? Like what do you think is a good idea? Things that you might need to know that's not an example of a problem, but like things that you think will be that'll come in handy. Quotient rule formula.
H versus 0.
Say that again.
Limit of H versus 0.
Oh yeah. Yep. So I'll just call that limit definition of dy dx.
Power rule.
Power rule, yeah.
Chain rule.
Implicit differentiation.
Oh, implicit, yeah. Yeah, good. Sometimes, some folks find it helpful to include, there's lots of space. Like, it's a 5x8, you could use both sides. I think it's historically, lots of people don't actually even use up all the space, so I don't even think you need to make it that cramped, Like, we've got what you have written down here might come close to filling up one side of the power rule. Some people I've seen in the past include, like, Pascal's triangle, like those things that can make some of the algebra a little simpler, for when we're doing that limit definition. Anyway, just sort of give it some thought, and one of the things I like to do, there's a practice test posted to Canvas, right? So right at the top module here, there's a practice test and also my solutions. So one of the ways I encourage people to kind of use these practice tests is, you're obviously working on the problem set and everything as well, but if you take time to kind of try to work on the practice test, just try to do as much as you can without referring to notes, and then places where you get stuck or these things that you have a hard time remembering, that might give you an idea of something that you want to include on your note card, or even some places where you might want a little bit more practice, or want to ask me some questions. If there aren't any questions, I don't need to take up any more of your time today, so I'll go ahead and let you go. If you have questions, please reach out and let me know. Otherwise, I'll see you all on Wednesday, and we'll talk about higher derivatives and finish up this chapter.